Okay, thank you everybody. I am so excited to be here to present on behalf of my co-authors some research that I did during my doctoral dissertation. I'm a little intimidated coming after that wonderful keynote speaker, but hopefully it'll go okay. So I am happy to talk to you about habitat partitioning with mesoscale features. So habitat partitioning is a strategy used by organisms to reduce competition. There's a theory in ecology called competitive exclusion theory that if two species occupied the same niche, one would outcompete the other. Competitive exclusion theory, if two species occupy the same niche, one would outcompete the other, and the weaker species would go extinct. And resource partitioning allows species with similar niches to coexist. In the Southern California Bight, where I did my research, we have 3 species of closely related baleen whales, which all rely at least in part upon krill. Blue whales, which of course are obligate krill foragers, fin whales, and humpback whales, which are more generalist. And one of the questions I hope to address with this study was, could mesoscale features be a part of their habitat partitioning strategy? So what do I mean by mesoscale features? I'm referring to eddies, fronts, and filaments that are on the order of tens to hundreds of kilometers long and persist for weeks to months. And these mesoscale features structure pelagic ecosystems, for example, by moving nutrient-rich water away from upwelling sites, encouraging phytoplankton growth, giving rise to the structure and phytoplankton patches we see in this ocean color image. And they're also important foraging hotspots for many species, including cetaceans. For this study, I focused on this region here, the Southern California Bight. And we used data from close to 2 decades of marine mammal visual surveys that were taken as part of the CalCOFFEE program. For those who may be unfamiliar with this stands for the California Cooperative Oceanographic Fisheries Investigations, and it's an oceanographic sampling program that goes out 4 times a year and has been running since the 1950s. So we've been doing marine mammal visual surveys on CalCOFFEE since 2004, and my study goes through data through 2021. So we had data from 64 quarterly cruises, so quite an extensive data set. Unfortunately, there were a few incomplete years where we weren't able to go out every season, including 2020 and 2021 for obvious reasons. So this is the CalCOFFEE station data map. We go from just north of Point Conception in the north down to just north of San Diego. The black dots are the oceanographic sampling stations, and we're looking for marine mammals on the orange lines as we transit between stations. So for mesoscale features, I used 2 different data sets. And the first one is looking at something called finite-size Lyapunov exponents, or FSLEs. These are showing regions of convergence. And we get this data from satellite altimetry. It's derived through surface velocity fields. And these FSLE ridges, which are in this image here, are the dark lines, show areas of convergence along fronts of filaments and around the outside edges of eddies. I also used the Mesoscale Eddy Trajectory Atlas, which is shown here. This is both from a random day in July 2021. In this image, the blue are the cyclonic or cold core eddies, the warm is the anticyclonic or warm core eddies, and the yellow is data that is not in an eddy. So if we put these together, we can see how they line up. You can see that the FSLE ridges are around eddies, but they're also in between along the fronts and filaments in the ocean. And in this bottom image, I'm only showing the FSLE ridges that have a strength of -0.1 or greater. These numbers are negative, so when I say stronger or greater, I mean more negative. And that indicates stronger convergence in these areas. So I looked at the FSLE intensity for each on-effort, on-transect cetacean sighting in our data, and also recorded the eddy position, if it was inside or outside of an eddy, and if it was in an eddy, whether it was a cyclonic or anticyclonic eddy. So that's the cetacean encounter data. And in order to test whether cetaceans were occurred at these features more often than expected by chance, I recorded the same information along the cruise tracks while observers were on effort, on transect, and looking for cetaceans. And I compared the data in the cruise tracks with what we'd see in a given cetacean species in the cetacean encounter area. For data analysis, I compared the FSLE data from cruise tracks and cetacean encounters using the Kolmogorov-Smirnov test, as well as plotted the kernel density estimation functions. For the eddy data, I used a binomial proportion test to look at the proportion inside of an eddy, as well as in cyclonic versus anticyclonic eddies. So today, very briefly, I'm just going to cover some of the baleen whales, which I talked to you about, and then mention a little bit about Dall's porpoise. Although in my dissertation chapter, I ended up covering 6 species across 4 different seasons. So back to the question I posed at the beginning, are mesoscale features used as a form of habitat partitioning? So I'm going to look at summer, which is the primary foraging season for baleen whales, and we're going to start with blue whales. On this map here, the black dots are those Cal Coffee oceanographic sampling stations that I showed earlier, and the orange dots are the cetacean encounter locations. We can see that blue whales occur throughout the Cal Coffee region, except for in the southwest offshore corner, as well as they're conspicuously absent north of Point Conception inshore. However, notice that they are biased towards the south of the Cal Coffee region. Now, looking at FS Lee intensity, we have here FS Lee intensity PDF, and more intense is to the right on the graph with the stronger negative numbers. And this is the FS Lee intensity of the cruise tracks. And if we compare that to the FS Lee intensity of the blue whale encounter locations, we can see that blue whales were encountered at stronger FS Lee intensities than we'd expect given by chance, and that this result was statistically significant from the Kolmogorov-Smirnov test, which is the p-value that I'm showing here. Now, there was a recent study that came out last year that looked at blue whales off Monterey, and they used satellite tag data, so they're looking at very fine scale movement. And they looked at FTLEs, which are closely related to FSLEs and show the same underlying physical structures. And they found the same results, or similar results. The light gray hump in the back is their background FTLE distribution, where the black line is the blue whale positions for all blue whales, and the red dashed line is the blue whale positions for blue whales that were actively foraging. And they're showing that these blue whales were at stronger FTLE locations than you'd expect by chance. So that's great because our results show the same thing for 2 different types of blue whales, but also crucially, they're 2 different types of data. They used fine scale movement from satellite tags, whereas we used visual surveys covered over almost 20 years. So let's look at the eddy data. Here we have blue whales. And we found that there was no statistically significant difference in the proportion of blue whale encounter locations within an eddy compared to the proportion of cruise track locations within an eddy. If we look at the type of eddy they were visiting in, we found once again that there was no statistically significant difference between the proportion in anticyclonic or cyclonic eddies. So now let's look at fin whales. They occupied a similar region to the blue whales in Cal Coffee. However, notice that they are biased towards the north. We saw most encounters on that northernmost sampling line. Like the blue whales, fin whale encounters occurred at stronger FSLE intensities than the background that we would expect by chance. But when we look at the eddies, we found that fin whales were more likely to be encountered within an eddy than we would expect based on the cruise tracks. And they were almost always encountered within a cyclonic eddy, not a anticyclonic eddy, which is significantly different from the proportion of cyclonic and anticyclonic eddies that were available for them on the cruise tracks. And finally, humpback whales. Please note that humpback whales in the summer in Cal Coffee are much less frequently present than blue whales or fin whales, and they're concentrated in that region just north of Point Conception, where we were lacking blue and fin whale encounters. Humpback whales are encountered at stronger FSLE intensities, but it's a little more ambiguous. We can see the peak of the humpback whale distribution is at higher FSLE intensities than the peak of the cruise track location, but they're missing from the very highest FSLE intensity around -0.2. And interesting, if we look at the proportion of encounters within an eddy, we found that not a single humpback whale encounter in our data occurred within an eddy during the summer. So tying that together, we can see that blue whales have a southern bias, fin whales have a northern bias, and humpback whales are found inshore north of Point Conception. Blue whales are stronger FSLEs, fin whales were also found as stronger FSLEs, while the situation for humpback whales is a little more ambiguous. Blue whales showed no preference for or against eddies, whereas fin whales were found preferentially within eddies and within cyclonic eddies in particular, whereas humpback whales were not found within eddies. Now I'm going to talk very briefly about Dall's porpoise. Dall's porpoise is a cold water associated species that we have in the California Bight, primarily during winter and spring. I showed in some of my other research, which I'm not presenting, that Dall's porpoises have really declined dramatically in the Southern California Bight, starting around 2014. We had a very large marine Pacific heat wave in 2014 to 2016, and sea surface temperatures have remained elevated since then. So we wanted to look at Dall's porpoise with mesoscale features to see if that could be influencing their presence in the region. And what we found is that in both seasons, spring and winter, Dall's porpoises are associated with stronger FSLE intensities. In particular, these very strong FSLE intensities here. Now, these are very rare in our data set. During the winter, only about 5% of the cruise track locations occur at this intensity or greater, compared to 14% of Dall's porpoise encounters. And in spring, that difference is even more stark, from 3.5 to 22%. So we know that they're targeting these features. That led us to ask, is this potentially why they are not in the Southern California Bight as recently? Maybe there's fewer good, strong FSLE ridges for them to target. So we compared years with encounters, showed here in black, with years without encounters, showed here in gray, and we found no, there was no statistically significant difference at all between the distributions. They're very similar. So this appears to suggest that although Dall's porpoise appear to target strong convergence zones, as shown by FSLE intensities, it's not a driving factor behind why they are with us or not. So in conclusion, strong FSLEs are targeted by bluefin humpback whales as well as Dall's porpoise. Bluefin and humpback whales show spatial habitat partitioning and use of different mesoscale features. And although Dall's porpoise targets strong FSLEs more often than expected, FSLE strength does not determine whether Dall's porpoises are in the region. And I just wanted to say thank you all for your attention. And also, I'm looking for a postdoc, so if you think we might fit, please contact me. Thank you.